Okay, let's wrap up momentum by talking about what happens when an object bounces off something else, which is a special case of conservation of momentum, and also two-dimensional collision. So let's talk about bouncing first. The key thing is when something bounces, that what happens is I go from a velocity initially in that direction to a velocity final in that direction. So this could be, for example, balls and bats in both softball and baseball, in which the ball starts out in one direction, ends up in another direction. Could be anything moving off a wall. Could even see, I don't know, maybe bumper cars, something like that, in which the cars come back at some angle. You can also see it actually in the game of pool if you get really, really good. The key thing here is that delta V is equal to V final minus V initial. And the key thing here is direction matters. Since momentum is a vector quantity, it has to have direction. So if I'm going to say that let's say that the VI is my positive direction, what I'm going to get is delta V is going to be equal to VF, but that's in a negative direction, minus VI. So I actually works out to be negative VI plus VF. And the negative sign is really only indicating that the direction has changed. So the delta V is actually going to be the sum of the two velocities. So be careful about that, because you're changing direction. So you get a bigger bump off it. And we have something we'll do in class to help you with that. Okay, let's look at an example problem. So a baseball hits a brick wall. The baseball's moving at 30 meters per second initially, and it has a 0.5 kg mass, and it rebounds out at 25 meters per second. What is the delta V? Well, here's where you have to get careful, and I think it may actually help to draw a little sketch of what's going on. You're coming in at 30 meters per second. You're going out at 25 meters per second. This is your wall over here. Delta V is actually going to be V final. Let's actually say that V final in this case is positive. So V final minus V initial. V final is 25 meters per second minus, well, but the 30 meters is in an opposite direction. So my change in speed is actually 55 meters per second. So when you get that, so it's really just the sum of the two. So if you get a bouncing problem, you can just simply add it up. Now, let's throw in let's expand it to make an entire problem out of it. How does the force on the ball and the wall compare? So in other words, while the ball's hitting, which one feels a greater force? Think about it. Same force. Now, which one, let's extend that a little bit, which one would feel the greatest acceleration? Well, the forces are the same, but don't forget that F is equal to F, so therefore MA is equal to MA, so the ball has a little mass and it gets a big A. The wall has a really big mass, so it gets a very little A. And the wall's attached to the earth, so the A is almost unnoticeable. So next question is, what is the impulse? Well, impulse is Ft, but Ft is also equal to delta P. And we know that delta P is mass times delta V. So therefore, I know that the mass is 0.5 kilograms. I know that delta V is 55 meters per second. So therefore, it's, now let me see, do that in my head. How about 27.5 kilogram times meters divided by seconds? So the impulse that's given to that ball is that much. So let's extend it one step further. if the ball was in contact with the wall for 0.05 seconds, how much force does the ball apply? So now I'm going to go to Ft is equal to m delta v. So therefore F is equal to m delta v over t. And by the way, this is a problem you could actually solve just from kinematics. You know A is delta v over t, so you could do it that way. But since we already have these other things, we have 27.5 kilogram meters divided by seconds, divided by, because I've already got m delta v, divided by the time of 0.05 seconds. That's big. I don't have a calculator. You can do that though. 27.5 divided by 0.05 is going to give you a really big number. And it should be a really big number. You're talking about a ball, traveling fairly fast, hitting a brick wall and bouncing off it. Next question. Is this an elastic or an inelastic collision? Well, think about it. An elastic collision, kinetic energy is conserved. In an inelastic collision, kinetic energy is not conserved. So therefore, this has got to be inelastic. It came in at 30 and left at 25. The Earth is so large that when I figure out the mass, I have to include the mass of the Earth and the wall. That's a significant number. So therefore, it's inelastic. Those are never going to give you the same kinetic energies. So therefore, it's an inelastic. Not perfectly inelastic, but inelastic. Okay, let's look at 2D collisions. All the laws that we had before still appear. So what I'm going to have is a pool game, and a lot of y'all have played pool at some point in time. I have a cue ball rolling into the 8 ball at rest. So that's my before picture. Afterwards, I have this. The 8 ball takes off at 5 meters per second at an angle of 30 degrees from the horizontal. Okay. So what I want to do, first of all, sketch the direction of the cue ball. Well, momentum has to be conserved. So we've always said PB is equal to PA, but now I can go one step further. PB in the x direction has to be equal to PA in the x direction. PB in the y direction also has to equal to PB in the x direction. Now here's the key thing to understand with that is two equations. Two equations gives you the power to solve for two unknowns. Now if we sketch the direction, well obviously the cue ball's got to go back over this way some way. Let's call this angle down here, let's call that theta. We don't know that, and we don't know that v either. So there's two unknowns. But I can get two equations, so I can solve for two unknowns. Now, I don't think on the AP test they're going to ask you to mathematically solve that. We may do a practice one, but I don't think they're going to ask you to do it because of the algebra involved. The math's not necessarily that hard, but the algebra can get sticky. So let's look at how we would solve it from an algebraically. So set up, but do not solve two momentum equations. Now, here's the key thing here is I think it probably makes sense. The way I do it is I'm gonna get a p table for the x direction and a p table for the y direction. Is I think probably the easiest way to do it. And then what I'm going to do is get an equation from each one of those tables. So let's take a look at it. So I have a Q, I have an 8, I have total. Over here I have Q, 8, and total. And I got a before, and I got a after. Remember, I'm going to do anything I can do mathematically, but anything I can't do mathematically, I'm going to leave formulas in. So let's do that. Do the same thing over here, before and after. Again, we're not going to solve this all the way. We're just going to look at what it takes to solve it. Q8 and total. So we have that. So now, let's look at in the x direction. Let me redraw it here so we can see it better. This is my Q. It's moving at 10 meters per second. This is the 8. It's at rest. So that's my before case. So let's do all the before cases. Well, here's the whole thing. In the before case, all of the momentum is in the same thing. Now, I didn't give you the mass of the cue ball, and the reason for that is the mass of the cue ball and the mass of the 8 ball are the same. So I could actually cancel it out. I could also just make up a mass. Let's make up a mass and say the mass is equal to 1 kilogram. That's a giant cue ball, but it makes the math easy since the balls are the same size. That makes life easier. So the momentum of the cue ball beforehand is all in the x direction. So it's going to be 10 units of momentum. 1 times 10. The cue ball beforehand has 8, so this is 0. Now afterwards is where it gets a little bit stickier to do this. Afterwards, what happens now is the cue ball is going to, this is my after case. This is the 8 ball. The 8 ball goes 5 meters per second at 30 degrees. The cue ball comes down here at some theta we don't know, and a v we don't know. So the key thing though is it's the x direction of this. So it's going to be v times the cosine of theta. Now I don't know that. I don't know either one of those, so I just have to leave it there. Now for the cue ball, it's going to be the x part of that 5, which is going to be 5 times the cosine of 30 degrees. Cosine of 30 degrees is 0.866. So 5 times 0.866 is going to be a little over 4, 4.3. So I have 4.3 meters per second. But here's the key thing. Since momentum has to be conserved, that's got to add up to 0. So what I have here is v cosine of theta plus 4.3 has to equal 0. That's one equation, but it's got 2 unknowns, so I can't solve it. So let's go to the y section. Now, the key thing for my before case is the cue ball's not moving in the y direction, so that's 0. Hey, the 8 ball's not moving beforehand in the y direction, so therefore it adds up to 0. So I know that has to add up to 0. So now, let's take a look at the after case. The after case is going to be this side of the triangle. It's the upward part of it, which is going to be 5 times the sine of 30. So 2.5. Now, afterwards down is going to be this side of the triangle. Oh, let me draw it on this picture. It's going to be this side of the triangle, which is opposite, so it's sine. Excuse me. Afterwards, yeah. So this is going to be v times the sine of theta. And I don't know what that is, but I know that this equation is valid. So I get v sine of theta plus 2.5 has to equal 0. I now have 2 equations, and it's solvable. I don't think they're going to ask you mathematically necessarily to do one of those. Sorry, I'll move it up a little bit so you can copy it. I don't think mathematically, because algebraically this can get a little bit sticky. It's not something you've done before. It's just a little bit of a pain. Key thing to understand in 2-dimensional collisions. P is still conserved. It's conserved in 3-dimensional collisions. If I had something happening out in space where things are moving at different angles altogether, P is still going to be conserved. The key thing is I can say the Px before is equal to the Px after. The Py before is equal to the Py after. And the reason I can do that is momentum is a vector quantity. The fact that it's a vector quantity means direction matters. So therefore, when things collide, if I have cars, for example, let's say I have a car going that way, and I have a car going that way, and I know that, well, obviously when they hit and stick together, they're going to go off some angle like that. But how much the angle would be depend on these 2 initial ones. Whichever one had the greatest momentum would dominate the crash. So let's go to a different color.